Okay. Hello guys. So this is your lecture 4, the cross product. So last time we have introduced the interior product or inner product or dot product. So that is a way to operate between two vectors. And now we're gonna introduce another operation between two vectors, right? So this is called a cross product. So I will go like this. I will define the cross product first, and then I will give what it actually means and how we can memorize it in a more intuitive way. Right. So for the cross product, it's very important to note here that cross product only happens in all three, or in three-dimensional space. So previously, when we talked about that product, I mentioned that you can define that for any space. You can define it for real number R, Cartesian plane R2, three-dimensional coordinate space R3, R4, any R would do. But in this case, it's only defined for R3. Okay. There is a very fascinating reason why that is true, but today we're not going to talk about that. We're going to talk about how we define cross product in R3. Okay. So again, given vectors u and v, those are three-dimensional vectors. Okay. The cross product is a operation between two vectors that gives you another vector. So u cross, listen, pronounced crossed. So u cross v is another vector, right? It is given by u2 v3. So this coordinate together with this coordinate, subtract by u3 v2, and so on and so forth. u3 v1 minus u1 v3, u1 v2 minus u2 v1. So first of all, the takeaway here is that the operation between two vector after taking cross product is another vector, right? Recall that in the dot product, when we take operation of dot product between two vectors, you'll get a scalar, right? So those are the difference between dot product and cross product. Now, this definition does not really make sense. For now, we don't know why we define a string vector like this, but there is some geometrical intuition behind that. So first of all, we are going to introduce why cross product is important. That is our geometrical interpretation. And then we are going to talk about how do we simplify this kind of string notation, these strange numbers, okay? And those are categorized in the algebraic simplification. All right, so first of all, let's talk about the geometrical interpretation of the cross product. So the intuition behind the cross product is the following problem. So again, given two vectors u and v, we want to find some vector w that is actually orthogonal to both u and v. Okay. If you think about that, it is quite natural in three-dimensional space. Given two vectors, then those two vectors gives you a plane, right? And there should be a vector that is normal to that is orthogonal to that. Of course, the direction can be either this way or this way. But anyway, we want to find that particular vector. So how do we solve that? Recall from our previous slide that whenever W is orthogonal to U, that means W dot U, the dot product, is 0. So again, I'll emphasize this again and again. This is a scalar, okay? Whenever we're taking dot product, the output is a scalar. So W dot U is 0, and W dot V is also 0. So those two gives us scalar equations like this. U1 W1 plus U2 W2 plus U3 W3 equal to 0. And the same thing happens for V. You can see that I underlined the W1 here and W2 and W3 because those are the variables. U1, U2, U3, V1, V2, V3 are given already. You now want to solve for W1, W2, W3. Okay, and the most basic way, the most intuitive way to solve this kind of three-variable equation is to eliminate some of the variable. In this case, I want to eliminate W1. So the natural thing to do is to multiply equation 1 by V1 here, and multiply equation 2 by U1 here, to make sure that W1 has the same coefficient in both equation 1 and equation 2. Okay? So after multiplying V1, you get this equation, U1 V1 W1 plus U2 V1 W2 plus U3 V1 W3 equals to 0. Okay? And the same thing happens for the second equation multiplied by U1. Now, as I mentioned, to eliminate the first variable here, we take subtraction and we get U2 V1 minus U1 V2 as the coefficient of W2. And as the coefficient of W3, you have U3 V1, U1 V3. Okay, so this equation is rather simple to solve. So let us sort of first solve a simpler equation to see why what I'm going to say is true. So say we're solving a x. Okay, let me use numbers. A x plus 3y equals to 0. So one of the natural solution would be something like this. 3 and minus 2, right? When x is 3, then y will be minus 2. So you can always choose the first number to be the coefficient of a second number, and the second number to be the minus of the coefficient of the first number, minus 2. So you see that I claim here that W2 and W3 can be solved by the coefficient here, U3V1 minus U1V3, and W3 can be the negative of this guy, which is U1V2 minus U2V1. Okay? If you plug those blue solutions back into whatever equation you want to say, 1 or 2, you will get W1 equals to U2V3 minus U3V2. So summarize those up, you will get that W1, W2, and W3 is actually indeed this vector. Okay? Of course, I have mentioned that it is a solution of this equation system because any scalar multiple will be a solution to this. So what I'm saying is that suppose you plug in 2, multiply everything by 2, this W1, W2, W3 is still a solution because the combination just give you 0 minus 2, which is again 0, right? So this W1, W2, W3 is just somehow a standard way to represent this kind of orthogonal vector, right? So basically what I'm trying to say is that the cross product is just a vector that is orthogonal to U and V, okay? Which is a particular combination of U1, V1, U2, V2, and U3, V3. And of course, any scalar multiple of that will be orthogonal to U and V. But we pick this one in particular because it is something that is nice enough for us to write it down, right? So let us recall this. So our intuition of doing this cross product is to find a vector that is orthogonal to both U and V. So naturally, this thing is just orthogonal to U and V, right? After giving that intuition, so we know why we are interested in this kind of vector. The second thing is algebraic simplification. We want to try to make things more compact. We want to make the definition more intuitive for us to memorize. So let us introduce some notation here. Here I'm going to define something that is called determinant. There is a long history of about determinant in mathematical study. I believe either you have already taken or you will take some linear algebra, then you will be having a lot of study on this kind of object. But for now, we are just borrowing the notations from the algebra world. So first of all, we define a two-dimensional determinant to be something like this, basically a 2 by 2 table with 4 numbers, okay? A, B, C, D. And we write a bar around it. And this is a quantity defined by A times D minus B times C, okay? So we multiply the main diagonal and we subtract the multiplication of diagonal term, AD minus BC. All right. And a three-dimensional determinant is defined recursively in terms of the two-dimensional determinant. So again, you put a 3 by 3 table within 2 bars, and it is still a scalar. The scalar is defined as follows. So we pick the first from here, A1, and we eliminate the row, the first row containing A1, the first row containing A1. Sorry, the first row containing A1 and the first column containing A1. And the remaining 2 by 2 determinant is put it here, B2, B3, C2, C3. Similarly, for A2, we eliminate the first row and the second column. So you get B1, C1, and B3, C3. And lastly, for A3, we have the first row eliminated, the third column eliminated. So B1, B2, C1, C3. Okay. And one thing you notice is that this here is of a negative sign. So there's an intuitive way of why this definition makes sense at this to some degree for algebraics or geometrists, but we're only borrowing notation here. So that is just leave it like this. This is the definitions, okay? So just to emphasize on how this thing works, let us do some example. So first of all, let's compute this determinant with 2, 4, minus 1, 3. So we compute the multiplication of the diagonal term, 2 times 3, minus the off-diagonal product. So it's 4 times minus 1. So that gives you 6 plus 4, which is 10. Similarly, by definition of this 3 by 3 determinant, we collect the coefficients 1, 2, 3 in the first row. And to determine the associated 2 by 2 determinant, for example, for this guy, you eliminate whatever row and column that the first entry is contained. So you eliminate the first row and the first column, you get this guy. For 2, you eliminate the first row and the second column, so you get 4, 3, 2, 6, which is here. Lastly, for the 3 here, you eliminate the first row and the third column, which you get 4, minus 1, minus 3, and 5 here. And again, don't forget, this is a minus sign, right? After doing so, then we compute the 2 by 2 determinant. So minus 6, subtract by 10, you get this guy. 24, subtract by minus 6, so 24 plus 6. 4 times 5 is 20. 20 subtract by 3. All right, so you get a bunch of numbers, and then you can compute those using your hand or using your calculator, okay? It turns out to be minus 35. So let us try to memorize this. You have a bunch of numbers, in this case 4 numbers, in this case 9 numbers, and those combination gives you a scalar, a single number, okay? Where a 2 by 2 determinant is defined by this quantity, and 2 by 3 is defined iteratively using the 2 by 2 determinant. All right. Now, how will that help us? So let us recall the definition for U cross V, the cross product. You have U2V3 minus U3V2, which can be written as this way, right? U2V3 minus U3V2. And we have that is the x coordinate. So you have I as the 1, 0, 0. If you guys remember that from the first video, 12.1. Similarly, for J, you have U1V3 minus V1U3, and you have a negative sign, right? So this whole thing is this thing, right? And that corresponds to the Y coordinate, so J. Lastly, this guy is U1V3, subtract by U2V3. So, actually, yeah, sorry, there's a typo here. This is U1. This is V1, U1, V1, V2, sorry. So U1, V2 subtract by U2, V1, which is exactly this term. And it is associated to the Z coordinate. So if you take a close look of this thing, it is actually a definition of a 3 by 3 determinant, right? It's actually this guy. So you see that we pick the first row I and compute the determinant here, right? We pick J and we compute the determinant here, together with a minus sign. And we compute K together with this determinant, right? So coincidentally, the definition of cross product satisfied through the definition of the 3 by 3 determinant. So that is in particular useful because it makes it easier to memorize the formula. So for example, if you okay, so maybe I should put it like this: if you have already memorized the 3 by 3 determinant in this format, which is kind of logical, then you instantly have the memorization of the cross product. So you see, as an example, let us try to compute 1, 2, minus 2 cross product minus 3, 1, 4. So through the definition of 3 by 3 determinant, you can write things like this: ijk in the first row, that's important, and 1, 2, minus 2 in the second row. minus 3, 1, 4 in the third row. Okay, those orders are fixed. Please don't try to alter anything. It will actually change the signature or something. But for now, we are not interested about the algebraic property of determinant. We're just introducing the definition of that determinant and the cross product. So in this case, it looks like this. And then by definition of determinant, you have this guy multiplied by I, this guy together with a minus sign multiplied by j, and the same for k. So you have 2 times 4, 8, plus 2, 10 in the x-coordinate. 1 times 4, 4 minus 6 minus 2, and we have extra signature here. So 2 in the y-coordinate. 1, 1 plus 6, so that's 7. And you can actually check our definition about cross product. So if I try to take the dot product between our u and our u plus v, which is 10, 2, 7, you get 10 plus 4 minus 14, right? Which is 0. So this guy is actually orthogonal to this guy. And you can do the same thing to find out that this guy is actually also orthogonal to this guy. So that is how we construct our cross product, right? So for now, you should have quite an understanding on how cross product work. We already understand the geometrical representation. We want to find some vector that is perpendicular, that is orthogonal to the given two vectors. And you can also represent that vector in terms of determinant, which is very elegant. Okay, so after definition, we come to properties. And again, as I mentioned, most of these properties are quite intuitive. If something is important, I will tell you guys, okay? So in this case, take u, v, w, three vectors, belongs to R3. And first of all, obviously, we have u cross v is orthogonal to both u and v, right? That is how we construct u cross v, right? Secondly, u cross u is always 0, whatever u is. 3 is kind of important. So unlike the dot product, recall that dot product satisfies u dot v is equal to v dot u, right? However, cross product is anti-symmetric, meaning that u cross v is actually minus v cross u. So in terms of geometrical language, taking a different order of cross product will give you this direction and this direction. They're in opposite directions, right? The rest of the properties 4, 5, 6 is quite natural following definition. So similarly as dot product, the scalar multiplication can be moved everywhere. So for example, you can take the cross product first and take the scalar multiplication, or you do the scalar multiplication and you do the dot product, sorry, the cross product, and so on and so forth. You also have several distributional laws. If you take the vector addition first, and then you take the cross product, it is the same as if you take the cross product first and you do the vector addition. Okay. Since for now, the two positions are not symmetric, so I state this twice. This is not completely equal to this because this is not equal to v plus w cross u, right? So I just state this twice to make sure that we know actually they are anti-symmetric, not symmetric, okay? Right, so here I present a proof about the first property, which is why u cross v is orthogonal to u. But again, that is kind of sort of by definition, because that is how we construct u cross v, but we can also verify directly. So say we want to verify u cross v is orthogonal to u, then you want to take the dot product between u and u cross v, right? And then we want to show that it's 0. So you see that u and u2, u3, and you have this large thing in the cross product representation of u cross v. So after computation, you see that there will be 6 terms, and there are 3 pairs of things which get cancelled, which get cancelled out, and eventually it is 0. So since the dot product between u and u cross v is 0, that means that they are orthogonal. And the exact same argument works for v, right? And as I mentioned, 2 to 4 follows from definition. So try to verify that them yourself. But as I mentioned, this is quite important. So you always have the anti-symmetric property. U cross v is always minus of v cross u. And in some sense, that is sort of intuitive from definition, because you see that This is u cross v, right? So in the say that in the first coordinate, it is u2 v3 minus u3 v2. If you are dealing with v cross u, then it should be v3 u2, sorry, v2 u3 minus v3 u2. And that is exactly the negative or the opposite of this number, right? And the same thing works for the y and z coordinate. So u cross v is always minus v cross u, which is different from dot product. Okay, and we make an important remark here, which is the right-hand rule. So we know that u cross v, supposedly u and v are not trivial, meaning that they are not like zero vectors. Then u cross v is some vector that is orthogonal to both u and v, right? Technically, there's infinitely many of those vectors because you can take different lengths, right? But there's only two possible directions. One is going this way, and one is going this way, right? And turns out that whenever we're doing cross product, we're always dealing with one way. And that way can be determined by the right-hand rule. So this is how right-hand rule works. First, you place u here. U is the first vector here. You place u here, and you place v here. So u is placed in your four fingers, u. And you curl your finger to v. So you see, this is my fingers. I curl it towards v. Then your thumb will be the direction of u cross v. So see that, for example, if I want to find v cross u, then it looks like this. This is v cross u. So the vector v cross u goes downwards. Okay, so this is called a right-hand rule. You take out your right hand and you point your four fingers towards the first vector, in this case u, and then you curl your finger u against the second vector v, and then your thumb will be the new vector u cross v. Okay, right. So that's the right-hand rule that helps to determine the vector direction of u cross v. Okay, now I'll introduce a important formula. So again, if we take theta to be the angle between u and v, then I claim that the magnitude of u and v, the magnitude of u cross v is given by the magnitude of u multiplied by the magnitude of v multiplied sine theta. So first of all, one thing might seem quite weird is that sine can actually be negative and positive, right? So there's no way that the length of some vector is negative number. But recall that previously in the dot product video, we defined the angle to be within 0 to 180. And we know that sine actually is always positive whenever theta is within 0 and 180, or 0 and pi. So this quantity is in fact positive, or to be precise, non-negative. So it makes sense to have this kind of result. And another thing that is different from dot product is that in dot product, we have u dot v being u v cosine theta, right? Because this guy is a scalar. But now u cross v is not a scalar. I'm claiming that the magnitude of u cross v is this guy, okay? So we kind of already understand everything about u cross v because the direction is determined by the right-hand rule, right? And the magnitude is defined by this formula, which is very, very nice. Okay, so as I emphasized before, proof is not really important. You can skip it to the next topic, which I will talk about here later, the corollary. But I present a proof here, which is kind of interesting because we also prove the nice identity that is called the Lagrange identity. So let's start the proof. I claim that we have this kind of identity. This is actually one of the exercises in your textbook. So I claim that whatever A and B and C and D are, those are four vectors in three-dimensional subspace. I claim that A cross B, which is a vector, C cross D, which is another vector. So this two vector taking dot product will be this quantity. So A dot C is a number, right? B dot C is a number, A dot D is a number, B dot D is a number. So this is a 2x2 matrix, 2x2 determinant. What I'm claiming is that A cross B dot C cross D will be this guy multiplied by this guy, subtract this guy multiplied by this guy. Okay, if you guys recall the 2 by 2 definition of determinant. So the proof is actually quite brutal. We just break out everything and we try to group things together to make this line representation. So you see that A cross B dot C cross D by definition looks like this. You have a bunch of determinant in your coordinate system, right? This is a definition of cross product. So you see that we have that. And then that product is doing entry-wise product. You get this with this, which is here, this with this. The sign does not really affect anything because it becomes positive, and this with this here. Okay. So in terms of pure numbers, you get A1B2 minus A2B1, C1D2 minus C2B1, and the same holds for every term here. So if we fill everything carefully, you see we'll get 2 times 2, which is 4. There is 3 of them, so 4 times 3, there will be 12 different terms. And we now have to develop some smart idea to group them together. So the first thing I want to do is I want to group A1C1. So see that what contributes A1C1? There is this guy, which is A1C1, B2D2, and there's also this guy, which is A1C1, B3D2. And do the same for A2C2 and A3C3. Each of them contains 2 terms, which is of the form BIDI, but the I only renders through everything which is not in front of them. So for instance, this is B2C2, B3C3. There's no 1, right? The same thing happens here. There's 1 and 3, no 2. There is 1 and 2, no 3. And we can also group together A1D1, A2D2, A3D3, and you get the exact same scenario. So the BICI inside the bracket, the I will not be in front here. So in this case, B2C2, B3C3, and it's A1D1. There's no 1 inside this bracket, right? And how is this grouping useful? So let us see the next equality. You can see that I add some orange terms here. And what is that valid? So you see that what I actually add here is I add A1, B1, C1, D1, right? Which is actually subtract here. A1, D1, B1, C1. The same thing happens here, right? So I plus A1, D1, C1, D1, subtract A1, D1, B1, C1. So nothing happens. The equality still holds. And why do I want to do this? That's because that I'm actually missing a term here, right? For the dot product. The same thing here with this 6 brackets. So after giving back what they want, we actually have A1C1 plus A2C2 plus A3C3. Those are multiplied by the same thing, which is this guy. You get that, subtract by, with the same logic, A1D1 all the way, multiplied by B1C1 all the way. But by definition, this guy is A dot C, B dot D, A dot D, B dot C, right? Writing them back as a determinant, you get what we want. Right. I know that's kind of complicated. It's a lot of algebraic stuff, but as I mentioned, the proof is not really important. I just want to present this because they're kind of interesting and provide a more straightforward way to explain what we are going to do next. So let us not forget what we want to prove is that the length, the magnitude of u cross v is actually u, the length, v, the length, times sine theta, where theta is the angle between u and v. So why is the formula above quite useful, the Lagrange identity? So if we pick A and C to be u, B and D to be v, we have u cross v dot u cross v, right? Which is the square of the magnitude of u cross v by some proposition in our dot product slide, right? But we have this formula by Lagrange identity, that is u dot u, v dot u, u dot v, and v dot v, taken determinant. And being precise, that is this guy times this guy, subtract by this guy times this guy. However, again, u dot u is actually the square of its own magnitude. The same for v. And u dot v and v dot u are the same. They're symmetric. The dot product is symmetric. So you get u dot v squared. However, we've learned in the dot product slide that u dot v is actually u squared v squared cosine. Dot product v is actually u v cosine, right? Taking square, you get this guy. So we can actually factor out the u squared and v squared here, which I get 1 minus cosine squared, and by the Pythagorean identity, that is sine squared. So at the end of the day, we have u cross v magnitude squared is equal to u squared v squared times sine squared. However, since everything is positive, you can take square root and you get u cross v, the magnitude will be the magnitude of u multiplied by the magnitude of v multiplied by sine theta. Okay, so there's that. I hope everyone enjoyed the proof. It is somewhat interesting through Lagrange identity. So now after that kind of proof, after that kind of formula, we can actually provide a more information about u cross v. So first of all, u cross v is 0 if and only if u is parallel of v. So I want to mention this notation. This means that whenever u is parallel of v, then this happens. Also, when this happens, this happens. Okay? So it says that both the terms on the left and on the right, they imply each other. Okay, now know that when is u parallel v, that means that you're either in the same direction or opposite direction, right? That's called parallel. So theta is either 0 and pi. However, sine theta, sine 0, and sine pi are both 0, right? So the magnitude of u cross v in this case will be 0. What vector has magnitude 0? Just the 0 vector, right? So that means u cross v is 0, right? And the same thing works back, because whenever this guy is 0, that means sine theta is 0. But the only angle within 0 and pi, the 0 and 180, to such that sine theta is 0 is either theta to be 0 or theta to be pi. So that means they're parallel. Okay. So we can investigate whether two vectors are parallel through the cross product. We will give a brief summary afterwards, but just that we have discussed in the product that you can determine whether two vectors are orthogonal through dot product, right? So orthogonality follows from dot product, and parallelity, if that's a word, follows from cross product. Another way to interpret it, u cross v, in particular magnitude, is actually the parallelogram determined by u and v. So let's try to define what this is. Given u and v, the parallelogram determined by these two vectors is actually just this two. Okay? And what is the area of a parallelogram? It's just space times height, right? In this case, base is v, the magnitude of v. The height is this guy, which can be computed by the trigonometric definition, is u times cosine theta. However, taking a closer look, this is just this guy, right? By our previous theorem. So indeed, the magnitude of u cross v is just the area of the parallelogram determined by u and v. Okay. So let us do some example for some computation exercise. So we have the points P, Q, R, S. P is 102, Q is 333, 758, and S is 527. So if you draw them closely, you will get P, Q, R, S. Those forms a parallelogram. And the fact that they form a parallelogram is can be validated through this kind of computation. You can see that, for example, PQ, the vector PQ, is given by 2, 3, 1, right? 3 minus 1 is 2, 3 minus 0 is 3, 3 minus 2 is 1. And that is the same as SR vector. The same thing holds here. So they're actually the same thing, the opposite side, meaning that they're a parallelogram. The side PQ is parallel to SR, and the side SP is parallel to RQ, right? Okay, so how do we figure out the area? As I mentioned, we can take two vectors, and figure out their cross product, right? So in this case, let us take SP and SR. SP again is just 1 minus 5 minus 4, 0 minus 2 minus 2, 2 minus 7 minus 5. And can do the same thing for SR. Then we take the cross product. So the cross product follows formal definition. You can try to do that yourself. You should get minus 6, 13, 16, 6, and 8. So taking the magnitude of that vector, you get square root of 269. That'll be the area of this parallelogram in a 3D space. Okay, so we have now provided more meaning about U cross V. U cross V itself, the vector, is just a vector orthogonal to both U and V. Its quantity, its magnitude is a more integer quantity. It's actually area of a certain parallelogram. Okay, now we can actually do the same thing for a two-dimensional parallelogram. But as I mentioned before, it is only natural to define a two-dimensional cross product. So how do we sort of extend this definition to two-dimensional? And actually, it is quite intuitive because a 2D plane, a two-dimensional Cartesian plane, is actually just a subspace of the three-dimensional coordinate system, right? So you can see that the XY plane is actually just embedded inside the three-dimensional coordinate system. So one can think of this. You can think of a 2D point as a 3D point, adding with 0 as a z vector, as a z coordinate, sorry. So there will be flat on the XY plane. And then you can do anything in 3D space. In this particular case, I take AB cross AD. Now both of those are three-dimensional vector, so you can do cross product, which is 0, 0, 0, 0, 0 minus 20, and the magnitude is 20. So that'll be the area formed by ABCD here, or ABCD here. And you can note that it is very intuitive why there is only a z coordinate here, because given the XY plane, the exact direction that is orthogonal to the XY plane is the z direction, right? Either plus z, either plus k or minus k. Okay, so that's natural why there's only a z coordinate here. And that's how we get the area for a parallelogram in a 2D space. Okay, now I think this is the last topic. Yeah, so last thing we're talking about is the triple product. So triple product is basically just something that involves three vectors. We define the u dot v cross w. And if you do the algebra, you will see that this guy is actually IJK. Looks like this, right? And u is just plugging in u1 here, u2 here, and u2 here. Why is that? Because let us go back to the definition. Where is it? Here. So if you take a dot product, say w1, w2, w3 with this vector, then it simply becomes w1, w2, w3, right? That's the definition of dot product, taking entry-wise product. And that is the same as replacing this by w1, w2, w3, right? So it is just natural to say that these two are the same, okay? U dot v cross w is just this determinant, a 3x2 determinant. And now I'm claiming that the volume of the parallel pipe determined by these three vectors is given by this quantity taking absolute value. So the bar here is the determinant bar, and the bar here is the absolute value, okay? Because for a volume, we don't really care about the signature, we only care about the quantity. So now let us see, first of all, what a parallel pipe means. Second of all, why is this true? So a parallel pipe determined by three vectors is basically the thing I drew here. You have U, V, and W, right? And the parallel pipe is just like parallelogram, but now you are in a 3D space. So you have this, this, and this. And that gives you a three-dimensional solid. Now, how do you compute this kind of volume? It is again just base times height, right? In this case, the base is not a segment, but a area. So first of all, what is the area? Area is V, the span by V and W, right? So it's V cross W taking absolute value. That is what we exactly just learned in the previous proposition. What is the height? So I make everything consistent here. You see that if you're doing V cross W, V is here, W is here. So taking care of the orientation of the right-hand rule, you get V cross W pointing upward, this case. So I want to project the U, the height U to here, which gives you U cosine theta, where theta is the angle between V cross W and U, right? So you have base times height. However, we know exactly that U dot V cross W is U V cross W cosine theta, right? And now if we don't care about the signature, we just take absolutely everything. So these two quantities should be the same. So it boils down to this sentence. The parallel path determined by these two vectors is given by U dot V cross W, which is given by this statement. Okay. All right, now this is a nice exercise. So we want to use the scalar product, which is what I just introduced, that U, V, W given here are coplanar. So coplanar means that those three lies on the same plane. And one thing to verify about the planar property is that if three vectors are coplanar, that means that U dot V cross W is zero vector. Oh, sorry, this is a zero, not a zero vector. It's a scalar. And why is that? Because you cannot actually give any volume in the parallel pipe, right? Supposedly, say in this case, U lies on this plane, and the only parallel pipe you span is some two-dimensional thingy, right? Which does not have any volume. So to check whether three vectors are coplanar, you can just check whether their triple product is zero. So as I do it here, if you take the triple product between U, V, and W, you get 1, 5 minus 2, 3 minus 1, 0, 5, 9 minus 4, and that thing gives you 0. So indeed, U, V, and W are coplanar. And in the other way around, if U, V, and W has non-zero triple product, then they must be not coplanar. So they're lies in different spaces. No plane can contain three of those vectors, right? Okay, that's a good exercise. So that summarizes what we have defined for vectors now, and this is practically all operational vector that we will see. So we have vector addition, which is very natural. U plus V gives you entry-wise addition. Scalar multiplication. If you multiply a scalar by some, multiply a vector by some scalar, then you just multiply them entry-wise. In 12.3, we learned the dot product, which is multiply entry-wisely and add things up. So you get a scalar. For the cross product, you have a very complicated definition, but you can memorize it by the determinant thingy, right? So let's have a little comparison about dot product and cross product. About a symmetry, dot product is entirely symmetric. U dot V is V dot U. For cross product, the symmetry is anti. It's reverse, meaning that U cross V is equal to minus V cross U. And that is kind of obvious by the right-hand rule. U cross V, V cross U. Okay. Now, as I emphasize a lot, the output for two vector doing dot product is a scalar, it's a number. For the output of two vectors doing cross product is a vector, right? Okay. Now there's two formula which is kind of similar. U dot V, the scalar, is given by the length of U times the length of V times cosine theta, where theta, of course, is the angle between U and V. And for the formula for U cross V, it is not U cross V, but the length, the magnitude of U cross V is given by the length of U times the length of V times sine theta. Okay? Now, about the orthogonality, the parallelity, whenever a dot product vanishes, the dot product is zero, that means that U and V are orthogonal. Whenever U cross V is zero, that means that U and V are parallel. Okay? So, yeah, that's pretty much a summary about the product and cross product. So I think our trip on the vector thingy ends here. We'll be seeing this more in chapter 16 when we're dealing with the surface integral and whatnot. But for now, that's all for the vectors, dot product, cross product. I hope you guys learned many things. All right. See you in your next video.